Here I will show how to create the stiffness matrix for a truss element and then use those partial stiffness matrices to create the assembly matrix for a structure that has two truss elements. In this picture, as you can see, I've created a structure that has two elements, element 1 and element 2. They're both truss elements, and it is created in a 2D dimension. Theta 1 and theta 2 are the angles between element 1 and element 2, and the x-axis counterclockwise, otherwise it should be negative. Stiffness matrix for a truss element can be seen at the bottom of the page. We have element factors such as Young's modulus E, cross-section area A, L, which is the length of the element. Then we have lower cases L and M, which are cos theta and sine theta respectively. First of all, we're gonna list our knowledge, or information or input data. Well, we need the Young's modulus, which is E, and then cross-section area, that is A, and then L. However, for these, we need to specify what our units are. So in this case, I'm going to use Newton and millimeter for force and length. So therefore, the unit for Young's modulus is going to be Newton per millimeter square, or we could write it as megapascal. For the cross-section area, it will be squared millimeter or millimeter squared. For the length, it will be millimeter. Then we have the angle, which we represented by theta. So I'll just type in angle. We're gonna give it as degrees, and then we need to form lowercase l, lowercase m, and EA over L fraction. Later on we will create new data as well. For time being, I use bold font to show these characters a bit more clearly. I'm using Mac platform, but I'm sure everyone can create the same thing in Windows platform with a little bit of change. So I'll just go ahead giving some numbers. For example, well, I'll use the material properties of aluminium. So the Young's modulus approximately 70,000 megapascal. Cross-section area, I'll give a random number for now, say 100 millimeters squared. For the length, half meter, so let's say 500 millimeter. Angle, for now, we don't know a certain angle, so again I give a random angle of say 30 degrees. Lowercase l is cos of theta, so I make L equals to cos, and then I choose the angle. However, Microsoft Excel uses radians, so I convert this to radians by time minute to 3.1415, which is pi, and then dividing it by 180. And similarly, for m, which is sine of theta, I do the same, so the angle times 3.1415 and then dividing it by 180. EA over L, well, we form the product, which is E times A divided by L. Now we're ready to introduce to the matrix the numbers we have, but as you can see, this stiffness matrix is a symmetric matrix relative to its main diagonal, and the numbers we need to create are simply L squared, M squared, and LM, and then we use negative of those numbers or those numbers themselves to create this matrix. Well, this matrix is 4 by 4, so I can always take an area that has same number of columns and rows. So say I'm going to create my 4 by 4 matrix here. So for example, this region. Just put a border around it so that this is the area I will use. Now I'm going to assume the first two columns, first column and then first two rows of this matrix represent the start point. Usually I assume start point to be the common joint, which in this case is 1. I merge these two and I call it 1. And then I merge these two again, I call it 1. I merge these two, calling it 2, and also these two rooms to call it 2 again. Well, and then I use the simple borders to specify each room that we used for start point and end point. Well, we could do the same things here just to specify our matrix a bit more clearly. Okay, just for sake of tidiness, I put all the numbers in the middle. As we discussed before, we need only 3 numbers, L square, M square, and LM. So I go ahead and create these numbers here. So for example, I'm going to call it L square as a title, M square again as a title, and LM. Well, L square is clearly equals to what we have for L to the power of 2, and M square again equals to M e to the power of 2 as well. LM is the product of L times M. Okay, so basically these are the numbers we will be using, so I highlight them. Now, first room or 1, 1 is L squared, so that is equal to what we have for L squared. On diagonal, main diagonal, the second character is M squared, so that is equal to this number that we have here. Next is L square and then M square followed by that. So that equals to L square, and this is equal to M square. We created our main diagonal. Now, next one on row 1 is LM. So that is equal to LM. This number is equal to minus of L square. This number is equal to minus of Ln. Next is Lm, so that is equal to Lm minus Lm and minus M squared. We have minus L squared minus Lm and we have Lm. On our last row we have minus Lm minus M squared and finally Lm. We just double check our matrix. This matrix has to be symmetric. So we have these numbers and then same numbers relative to the main diagonal. And obviously these two numbers are equal, so are these two numbers. So this matrix checks out. We created the main part of the stiffness matrix. We need to still time it by the factor EA over L to finalize the stiffness matrix. To do that, I copy this area in the same page. Well, as a result, we will have lots of zeros because these numbers are related to irrelevant fields, so we just delete them. Now, I will make this room equal to what we have on the relevant field, time by EA over L, but since I've decided to extend this formula to all of the rooms to avoid repeating writing the formula, I will just put a $sign next to B and next to 9. This way, when we extend the formula, it will take EA over L from the same room. So we just double check, for example, this room. If I click on it, yes, it has taken this number and timed it to EA over L from B9. Well, that finalizes the stiffness matrix for element 1. I just do a bit of highlights. For example, I would simply say K1 K1 equal to that highlights our first matrix. Now, again, you could do a lot of tidying up. For example, I'd like always to highlight these area with different colors, such as light blue, and then I could give, for example, light green here, and same color, and this one. Well, the reason I gave same colors to these two fields because they're essentially the same number. K12 is always the same as K21. Now, as you can see, I've created the stiffness matrix for element 1. I will copy this on the same page. I rename this to element 2. First of all, we call this element 2 as well. The formula and functionality wouldn't change, however these numbers may change. Well, if you have different material for element 2, say if you've got steel, so 210 thousand megapascal, cross-section area 120 for example, and length 600, and theta, say it's 70 degrees, and it will automatically change the numbers on the stiffness matrices. So for example, if you just change the angle from 70 to 60, as a result it will amend all the numbers. Nonetheless, the functionality doesn't change, the formula is still the same. So far what we've done, we've created stiffness matrix for partial elements. Nonetheless, we're aware that we have a structure that we have to deal with. Also, I forgot, we need to change these numbers to 3 because our second element has nodes 1 and 3. Now, next step is to create the assembly matrix for the whole structure that contains element 1 and 2 and shares the joint 1. So I create a new page, I call it assembly. Well, for the assembly we need a matrix of 6 by 6 because we have three nodes or joints in this structure, and each joint has 2 degrees of freedom, so 3 by 2 is going to be 6, a 6 by 6 matrix. So again, similarly, we choose a 6 by 6 field, so that's 4 and 6, and we highlight the area. Now again, same here, we merge these fields to name them after the joints. Well, this procedure is not essential, like putting these numbers here. However, it always makes the work field much clearer, and we are fully guided. And that's it. So at the moment we're going to form 1, 1. Well, 1, 1 because it's a joint. So it's a common joint between element 1 and element 2. Then 1, 1 will take the numbers from element 2 and add them to the corresponding numbers in element 1. So in assembly, we will say this room is equal to this number from element 1 plus this number from element 2. And because the formula is the same, the combination is the same for all these 4, we just extend the formula. So if I double check it, so this room, for example, takes G16 from element 1 and G16 from element 2, so which are these two numbers, G16 from element 1 and G16 from element 2. Next one is 2, 1, which is going to be the same here. So for 2, 1, we say is the same number from element 1. There is no 2, 1 in element 2, so again we extend the formula. Well, similarly, again, for 1, 2 or 2, 1. As I said, 2, 1 or 1, 2, it doesn't really matter how we label them or how we pronounce them, because they're always symmetric and they're going to stay symmetric. 2, 2 is this field. We take the number from element 1 again. And we extend the function. Next room is 1, 3 or 3, 1, doesn't matter. Will be taken from element 2 only, because element 1 doesn't have that. And similarly to 3, 1 or 1, 3 from element 2, function extended. Our next one is going to be 3, 3, which is this field. That will be taken from 3, 3 in element 2. And we extend it. Our next field is 2, 3 or 3, 2. 2, 3 or 3, 2 doesn't exist because there is no element between the points or joints 3 and 2. So we will easily substitute these fields with 0. Okay, I'll just tidy up these. So what we've done, we've just simply created a stiffness matrix for a structure that contains 2 truss elements, and it's mapped on a 2D or 2-dimensional coordinate system.